Okay. Is the slides visible?
Yes, sir.
Yeah, so in the last class, we introduced ourselves to Unit 2, that is enhancement in spatial and frequency domain. Uh, what we actually understood is there is two ways of doing it. Either I can do it in spatial domain or I can do it in frequency domain. Um, of course, while doing it in frequency domain, I need to take the image from the spatial domain to the frequency domain, for which we will use two-dimensional discrete Fourier transform. So we understood how spatial domain representation, spatial domain processing is done. So I'll use a window, and this window will run from left to right till the corner, and you will take a decision based on the weights on the window, and the window size could be anything. Usually it will be odd size, something like 3 cross 3, 5 cross 5, or 7 cross 7, but that is not a restriction. I can even have 2 cross 2 window also. It can be as simple as 1 cross 1 window. That means I'll just take every pixel and process it. In such case, we call it as point processing. When I take a pixel and process it, one of the simplest thing we took is converting a gray shade image into a binary image by just using a simple transformation function, as you can see here. Below the threshold, you will make all the pixel values as 0. Above the threshold, you will make them as high. So I'll have only two levels, black and white. And some of the basic transformation functions uh, we actually discuss here. The first one, which is very important, is negative, finding the negative of an image. So what you do is you just replace every new pixel by this value L minus 1 minus R. That means if R is 0 and I am using 256 gray levels, 256 minus 1 is 255, so 255 minus 0 is 255. So that means black pixel will become white pixel and white will become black. As you can see in this mammogram image, white pixel here has become black here. Okay, so whenever there is such any image where you have a very small white region which is surrounded by or dominating a black region, to view it better, we use a simple technique called image negative. So as you can see, now this could be easily located, and probably this would help a doctor in taking some decisions. And in your on-ramp course also, I think you would have seen whenever I am recognizing the text, we used this type of negation operation. IM complement is used to convert a binary image from maybe getting a negative of a binary image. So IM complement is a command. I think during the course you would have learned that. Now let us see a next um, transformation function called logarithmic transformation. Now, as the name itself says here, uh, the output pixel or the processed pixel is calculated using logarithm of the input gray level. So there are two things that you have to understand here. I'm not just taking log of r, I'm taking log of 1 plus r. The reason because all of you know that the gray level r can be 0 also. So if I don't add 1, then log 0 is a problem. All of you know that. So to take care of that log 0 problem, this 1 is added. So that is one important observation you have to take. And you know, if you just add 1 to any gray level, that hardly makes any changes in the value, because a 0 and a 1, you know, both of them look dark to you. So just adding 1 will not modify the data. That is why this is allowed. So 1 is added to take care of the log 0 problem. And there is a constant C here which will help you to keep the output gray level range in the same range as that of the input gray level. Because you know, for example, if R is 255, then this will be log of 255. So log of 255 will be some number. So if I want to make that equal to some output gray level, I can choose this constant C. I'll explain this with an example in the next class, may not be today. Um, Now here C is a constant, and this constant is calculated based on the required output gray level. Now what you should notice here is uh, where is it used? That is very important. Now whenever you have the input gray level having a very narrow range, okay, that means assume that I have a input gray level range from say 0 to 10, that's the maximum. Now to convert it into a wider range, okay, we normally use. Just carefully observe the graph for logarithmic transformation. This is a graph. This is a graph. So what you notice here is a very narrow range of input gray levels. See, from for example, from 0 to say some 10 or 15, you can observe the output gray level is taking a range from 0 to this much. Okay, so a very small range here is mapped into a wider range. Okay, then when I go to the higher side, you can observe here a very wide range. If for example from almost this value to this value, it is only mapped to a very narrow range here. Okay, so that is exactly what it says. It maps a narrow range values to a wider range, and opposite is true for higher values of input levels. That means you can just map exactly depending. For example, darker pixels, okay, what you have will be brightened, and brighter pixels, okay, because in fact these things, so you can just see it will take a very narrow range here. Now why we do this? Because there are cases where in fact a good example is, suppose if I take Fourier transform of an image and try to plot the Fourier transform. Okay, um, let me just demonstrate it using MATLAB. Hope I have some. Okay, even if it is not there, I can probably run a code to do that. Mm, Okay, I'll just read some image and convert it into gray and show it. Let me just do that. So I think I have to change the. Okay, so this is the child image that all of you know. Now what I'll do is I'll take Fourier transform of this image. So I'll do it on the command window here only. So let me just take capital X equal to, so the command for doing Fourier transform is FFT2. So FFT2 of small x. Okay, this is how you can do the Fourier transform by just using a simple command FFT2. So what I have done is I have taken Fourier transform of an image. Now you know Fourier transform will have both in fact it's a complex quantity, so it will have the absolute value, it will have the angle. So I'll just take x absolute, that means the magnitude portion. There is a command which is this abs of x. Okay, now suppose if I show this as an image, what I am doing is I am just showing the magnitude portion of the image. I think I have to change, I have to use unsigned integer. Sorry. So you could see that in fact I think better observation is if I use hopefully matte to gray, it would be better. Let me just try that. Yeah. So carefully observe, what you see almost is completely dark image. In fact, if you observe very carefully, in the corner here you have a white dot, which you don't see actually. I'll tell you why it is. So let me just show you what is the maximum value of this absolute value of the Fourier transform. This is a command, max of x apps. This will give you the maximum value. Observe here, the maximum value is 30534935, and I'll also see what is the minimum value. See, the minimum value is 0.7649. Now when I plot 0.7649 and 30534935, both of them on the same plot, you, because you know 0 is dark and highest is white. Actually in the corner here you have a white dot here. I hope you can notice it. So this is because normally the zero frequency component will be high. uh, in fact this value is actually the first value, 1 comma 1. Observe. So what it means is, when I take Fourier transform of an image, I have a wider range from 0 to so much high value. So what happens is, this will be plotted as white and all other values look 0. That is exactly what is happening, and I think in my slide also you would be seeing. In fact, here we have used a centering in fact command to center the Fourier transform, which I'll explain it in the next class. So in the center you will see a white dot, and neighboring pixels are almost seen to be zeros. The reason, because I have a very high value which is seen as a white dot. Compared to this high value, other values are dark. So when that is the case, if I use a logarithmic transformation, what happens is, log of a very high value, it gets compressed. So what I can do is, I can use, we will do this calculation in the next class. So what we will do is, for example, 30534935, this should be 255 for me. Okay, and the minimum value 0.7649 should be 0. So for this to be 255, I will use this equation. So the input value is 3053, etc. So that large number, log of that you will get some value, and I'll calculate the constant C such that S is equal to 255. That means the highest value will become white, and since it is using this particular graph, so the narrow range of pixels will be whitened. That means that's what you are observing here. You can observe that the narrow range of pixels, they are brightened here. That's why you are able to see them. Okay, and a very higher pixel value, it is just compressed. That is why, compared to the whiteness here, the whiteness here is less. So I hope you understood how this graph is taking care of that. So whenever I am displaying this type of images, okay, that means um, uh, particularly for showing Fourier transform of an image, which is a very important application, we use logarithmic transformation. That means I will map a very narrow range values to the wider range, and uh, opposite is true for higher values of input levels, and this is used to expand the values of dark pixels and to compress higher levels. So that's exactly what has happened. So the dark pixels are expanded and the brighter pixels are compressed. That means very high value is made equal lesser bright, so that all of them can be displayed on the same range. This is just like using logarithmic log chart or semi-log sheet that you have used to plot the frequency response of an amplifier. Why we did this? Because for a large change in frequency, there is a small change in the amplitude of the amplifier, or the output of the amplifier. So to compress it, we use the logarithmic scale for the frequency and linear scale for the amplitude. I hope you remember this when you did the lab in third semester. Okay. So with this, let us just close for today. And uh, uh, I think all of you know that next week you have first test. So the portions for the first test is Unit 1 again, complete Unit 1. And there will be multiple, in fact, patterns of the question paper which we will be sharing in the link. But all of you should join the link. In fact, I'll be sharing the link to the question paper through your email, official email ID. But all of you should log into the uh, okay, Cisco WebEx platform and take the quiz. It is a proctored test, so you should be keeping your camera on, and you should make sure that your writing area is visible to the invigilator. Any deviation, probably the case will be taken to the malpractice committee. So don't give room for that. Prepare well. If there are any doubts or clarifications, let me know. I can definitely explain. I think I have shared all the information about the course, like the slides I have shared,